Welcome to our Quantum Deep Dive.
Hello.
Today we're embarking on a really fascinating journey into the mind of a truly pivotal figure in theoretical physics and quantum technology, John Philip Preskill.
That's right.
Our guide for this deep dive is a comprehensive essay from Yorgo Schneepat, and our mission today is basically to unpack the biggest insights into Preskill's amazing career and his vision for quantum science.
And what's really compelling, I think, is how Preskill has consistently connected the really abstract world of fundamental physics with practical, world-changing applications.
Yeah.
We'll explore how his work has really redefined the foundations of quantum computing and information theory, but also pushed our understanding of the universe itself. So by the end, you should have a clear, concise, and hopefully captivating idea of why he's such a monumental figure.
It's always insightful, I find, to trace the origins. So let's start there. Who is John Philip Preskill? What set him on this path? He was born in Highland Park, Illinois, 1953. Grew up where intellectual curiosity was really valued, right?
Absolutely. That early environment, his education, it laid an incredibly strong foundation. He was clearly exceptional in math and physics early on at Highland Park High School, then went to Princeton, focused on theoretical physics, but his passion really seemed to cement during his PhD at Harvard.
Okay.
And he was mentored by Steven Weinberg, one of the greats of the 20th century.
Wow, yeah.
His dissertation in 1980, Unified Theories in Cosmology, already showed his analytical depth, tackling really big questions about fundamental forces, the universe's beginnings.
So he starts deep in quantum field theory, even string theory. Exploring tiny particles, the fabric of space-time, what was the trigger, the moment that pushed him towards quantum information science. Seems like quite a shift from cosmology.
Well, if you connect the dots, Preskill had this profound insight. He recognized that the challenges particles face, their stability in exotic environments, like in quantum field theory, were actually analogous to the problems of preserving delicate quantum information. He saw that maybe the universe itself was teaching us about error correction, in a way.
Yeah, interesting.
He realized that keeping information safe in quantum systems mirrored these fundamental challenges in quantum gravity, especially concerning black holes.
Right.
This kind of interdisciplinary thinking became his signature, really, and it led directly to his groundbreaking work in quantum error correction. It was a real pivot.
That leap, connecting error correction to fundamental quantum mechanics, that feels really key. And this is where it gets super interesting for quantum computing, right?
Exactly.
Quantum error correction is one of his biggest contributions. We all get file corruption, errors are annoying. But in the quantum world, with these super sensitive qubits easily getting messed up by their environment, decoherence, you called it?
Decoherence.
How do you even start correcting errors without just destroying the quantum information? It sounds almost impossible.
It's a really, really good question. Classical error correction, it relies on redundancy, right? Making copies.
Yeah, copy the file.
But quantum mechanics has this famous no cloning theorem. You actually cannot make a perfect copy of an unknown quantum state.
Ah, okay. Big problem.
Huge problem. But this is where Preskill and others too made a monumental breakthrough. They developed protocols like the Shor code, the Steen code.
Heard of those.
And the basic idea is you can protect the quantum state, but you do it cleverly. You encode it into a higher dimensional Hilbert space.
Okay, what does that mean practically?
Well, imagine instead of just one qubit being 0 or 1 you distribute that single logical qubit's information across several physical entangled qubits, maybe like 1000 or a 111.
I see. Spreading it out.
Exactly. The genius part is, even if one of those physical qubits gets hit by noise, say a bit flips or its phase gets messed up, you can figure out what went wrong and fix it from the collective state without directly measuring the fragile information itself.
Okay, that is clever.
It really is. Without these methods, honestly, large-scale quantum computation would just be a pipe dream because qubits are just too darn sensitive to noise. It literally created the foundation for fault-tolerant quantum computing.
And he also dug deep into quantum entanglement, Einstein's spooky action at a distance. Still baffling to many.
How did Preskill help us understand and, crucially, use this weird phenomenon, turn it from weird theory into a tool.
He was absolutely instrumental there. He showed entanglement isn't just spooky, it's an indispensable resource.
A resource.
Yeah, for quantum computing, for cryptography, communication. Think about protocols like BB84 for quantum key distribution.
Right, secure keys.
It uses entanglement, basically. If someone tries to eavesdrop, the entanglement gets disturbed and, it's inherent security.
Or quantum teleportation, not like Star Trek, but transferring a quantum state from one place to another using shared entanglement.
Got it.
Preskill's work wasn't just descriptive. He helped develop ways to quantify entanglement. Measure it. How much entanglement do you have? How useful is it? Turning it from a concept into something you can actually measure and use technologically.
What's really bold, though, is connecting quantum information to quantum gravity, black holes. The whole information paradox thing from Stephen Hawking, suggesting information gets lost forever, that messes with quantum mechanics, right?
Oh, absolutely. It fundamentally contradicts quantum mechanics, which says information must be conserved. This was a huge debate, really high stakes in physics.
So how did Preskill jump into that?
Well, Preskill was a real pioneer in arguing, quite forcefully actually, that information is not lost.
Okay.
He argued it stays stored somehow in really subtle, complex correlations within the Hawking radiation, the stuff black holes are predicted to emit. He famously made a bet with Hawking and Kip Thorne about it.
He won that bet, didn't he? Eventually.
Yeah, he did, yeah. Hawking conceded later. And Preskill's idea got support from things like the AD-SCFT correspondence.
That's the holographic principle idea?
Sort of, yeah. It suggests information about the inside of the black hole might be encoded on its surface, like a hologram. Preskill helped show how these ideas offered a way out of the paradox.
Wow.
His stance and the eventual shift in thinking really showed that quantum information isn't just about computers. It gives us deep insights into the universe's fundamental structure. It connects quantum mechanics and general relativity.
Amazing stuff. But beyond the pure research, Preskill is also known as a great educator and institution builder. Tell us about the IQIM at Caltech, the Institute for Quantum Information and Matter.
Right, IQIM. He founded it and directs it. It's really a world-leading center for quantum information research.
What makes it special?
Well, it's not just a lab. It's designed as this vibrant, interdisciplinary hub. It actively brings together physicists, computer scientists, mathematicians, material scientists, people who didn't always talk to each other.
Breaking down silos.
Exactly. And under his leadership, IQIM has driven breakthroughs in quantum algorithms, topological quantum materials. These are potential candidates for better qubits.
Mm-hmm.
He's really shaping the next generation of quantum scientists there, connecting fundamental theory with practical innovation. It's where theory meets experiment.
And his teaching, it sounds like he makes incredibly complex stuff accessible. How does he do that?
He fosters this very open, very supportive atmosphere. He encourages creativity, independent thinking. His lecture notes on quantum information, they're legendary.
Never know about those. Available online.
Yeah, freely available. They're just a masterclass in clarity, mathematically precise, but also really intuitive. Great for beginners and experts alike.
That's fantastic.
And beyond the classroom, he uses platforms like his blog, Quantum Frontiers, and public talks. He has this knack for distilling complex quantum science for a wider audience. He inspires not just researchers, but innovators, policymakers, the public. He's a great communicator for quantum.
He certainly is. And he coined that term, NISQ, Noisy Intermediate Scale Quantum, back in 2018. It's everywhere now. What exactly does this NISQ era mean for quantum computing right now?
Yeah, NISQ. It describes this crucial kind of transitional phase we're in, where quantum computers have, maybe 50 to a few hundred qubits, enough to do things classical computers struggle with.
Okay.
But they're still very noisy. They make errors. They don't have that full, robust quantum error correction we talked about earlier.
So intermediate scale and noisy.
Exactly. Preskill coined it partly to manage expectations, provide a realistic map. He sees these NISQ devices having huge potential, but for specific things.
Like what?
Like quantum simulation for chemistry or material science, discovering new drugs, new catalysts, or tackling complex optimization problems, maybe in logistics or finance, even accelerating some machine learning tasks.
So not universal computers yet, but useful for specific niches.
Precisely. The idea was, even with limitations, they could offer real advantages now before we get the fully fault-tolerant machines, driving progress step by step.
Okay, so understanding NISQ, what does this mean for actual applications? Short term with NISQ and then longer term.
Short term, NISQ could genuinely, maybe revolutionize drug discovery, help design new battery materials through those simulations classical computers just can't handle, maybe solve some tricky optimization problems.
Tangible stuff.
Yeah, potentially quite impactful. Longer term, though, with fully error-corrected quantum computers, that's a whole different ballgame.
How so?
Well, they could break most current encryption, like RSA, that's huge. It forces us to develop post-quantum cryptography.
Right, the race is on for that.
Absolutely. They also promise truly secure communication with advanced quantum cryptography, and they might unlock completely new science, allowing calculations in high-energy physics or quantum gravity that are just impossible today.
So a whole spectrum of impact.
Definitely. From near-term specific advantages to potentially transformative shifts down the road.
With that kind of power comes responsibility, though. And Preskill seems very aware of that, talking about ethics in society.
He absolutely is. He consistently highlights the societal side. He emphasizes several key things.
Right.
First, the urgent need for that post-quantum cryptography to protect our data. He's quite explicit about the risk.
Makes sense.
Second, the potential for major job market shifts. We need proactive reskilling, education programs. Third, the risk of widening inequalities if this tech isn't accessible globally. He advocates for openness, cooperation.
Important points.
And finally, he acknowledges the deep philosophical questions quantum mechanics raises about reality, about information. He urges a broad societal discussion about how we navigate this quantum age responsibly.
It's good he's bringing that into the conversation. Now, his impact is obviously huge, and he's received a lot of recognition. What are some key awards? How do his peers really see him?
Oh, the list is impressive. He got the Kavli Prize in Nanoscience in 2019 specifically for the quantum error correction work.
Right.
The Dirac Medal in 2020 for bridging quantum info and theoretical physics. He got an APS award for public communication, too, which says a lot.
Yeah, it does.
He's in the National Academy of Sciences. His collaborations with people like Hawking, Susskind, they show his standing. And his papers aren't just cited. They're foundational texts students learn from. He's truly one of the most influential figures globally in this field.
And how has he specifically influenced public understanding? Quantum stuff feels so abstract sometimes.
His Quantum Frontiers blog is a perfect example. He makes complex science engaging, translates jargon into insights. He's a sought-after speaker, known for clarity, even humor. That NISQ concept, for instance, wasn't just academic. It really shaped how industry and governments think about near-term quantum potential and where to invest.
Gave them a handle on it.
Exactly. And he actively pushes for education programs, inspiring the next generation, making sure they understand the implications too. He's a real bridge builder.
Now, like any visionary pushing boundaries, his career surely had challenges, maybe controversies. Were there points where his ideas faced pushback?
Oh, sure. Science thrives on debate. His role in the black hole information paradox was certainly challenging. Arguing against Hawking initially was a big deal.
Right.
There are also ongoing, very practical questions about actually building fault-tolerant computers using error correction. The theory is sound, but the engineering is incredibly hard with today's noisy qubits.
The scaling challenge.
Exactly. And even his NISQ idea has faced some critique. Questions about whether the near-term advantages are sometimes oversold.
Okay.
But these things show science working, right? It's dynamic. And Preskill has always engaged with these debates, welcomed the scrutiny.
But despite those challenges, the debates, his long-term significance seems undeniable.
Utterly undeniable, precisely. His fundamental work on quantum information theory, error correction, entanglement analysis, it's the bedrock. It's the blueprint for future quantum tech. And his interdisciplinary work connecting quantum mechanics and gravity, that continues to open new doors for understanding the universe. He's not just a scientist who published papers. He's profoundly influenced how quantum science is done, taught, communicated. He shaped the whole landscape.
So wrapping this up, what's the big takeaway?
Yeah.
John Philip Preskill's career, laid out so well in Yorgo Schneppet's essay. It really feels like a testament to, well, intellectual curiosity, sheer dedication, and the courage to connect seemingly separate fields. He truly is one of the key figures shaping our quantum future.
Absolutely. And his legacy, it goes beyond just the scientific discoveries, profound as they are. It's also in fostering that open, collaborative research style.
Yeah.
In his ability to communicate quantum complexity to everyone, and in championing the ethical, responsible path forward for these powerful technologies.
It definitely leaves us with a thought to chew on. As we stand right here on the edge of this new quantum technological era, what's our collective responsibility? How do we ensure this incredible knowledge actually benefits everyone and guides us toward a more informed, maybe more equitable future?
A crucial question.
Thank you for joining us on this quantum deep dive. We really hope you feel much more informed about the visionary work of John Philip Preskill.
Hope so.
And if you'd like to explore more of Jurgo Schneppat's insights, you can visit schnepppat.de.
Check it out.
Until next time, keep diving deep.